So thank you very much for the organizers for giving me the opportunity. And the title of my talk is Biomimicry and Nanomaterials, and I rather call it even the plant age. Now, talking about the plant age, I'd like to quote the former Minister of Oil of Saudi Arabia. Once said that the Stone Age ended up long before we ran out of stones. And the oil age will end long before we will run out of oil. And I'm going to say that for a good reason, because nano-biomaterials are so much better. And I'd like to start with a few examples, but before that, I think that we should not be so surprised. And why is that? Because all these synthetic materials that we've been using in the last 200 or 300 years from the beginning of modern chemistry and industrial revolution were developed over 300 years, and that's not a lot of time. While nature had 3 billion years to develop some of the most amazing materials that we wish we had in our possession. In fact, synthetic materials are used a lot even in our body. Orthopedic surgeons, they really love to take synthetic implants and screw them and glue them into our body. And I'm going to say that this is not a great idea for a simple reason. Synthetic material fail, just as like this plastic fork, that is not strong enough for its performance. But in a way, there are other synthetic materials which are very, very strong. The problem is that they do not fit their surrounding tissues, and therefore, that's why they fail. But the real reason why it's not a good idea to put these synthetic materials in our body is because in nature, things are done differently. In nature, there is no one there that takes my head and screw it into my neck, or take my skin and glue it onto my body. In nature, everything is self-assembled. Every living organism, whether it's a plant, or a fish, or a human being, or insect, is composed of cells, and the cells contain DNA, and the DNA encodes for nano-bio-building blocks. And these nano-bio-building blocks, many times there are proteins, other times there are enzymes that make other things like polysaccharides or fatty acids. And the common feature of all these nano-bio-building blocks is that, surprise, they don't need us. They recognize each other and self-assemble into scaffolds on which cells are proliferating and organizing into tissues. They are organized into organs, and together the organs, that's the organism or life. So we at the Hebrew University, about 14 years ago, in my lab, decided to focus on probably the most important nanobiomaterial for us, for human being. And that's collagen. Now, why collagen? Because collagen accounts for about 30% of our dry weight. We have nothing more than collagen in our body. I can give you a few examples. Bone is about 50% collagen, 50% minerals. Tendons and ligaments, close to 100% collagen. So I always like to say that anyone who would like to have materials to make replacement parts for human being, he needs collagen. But admittedly, even before we started our research 14 years ago, there were already on the market, in the clinic, more than 1,000 different medical implants that are made of collagen. You know, simple things like dermal fillers to reduce wrinkles, augment lips, artificial meniscus, as you can see, bone grafts, and even the leaflets of heart valves, all made of collagen. So you should ask me, well, why bother then? You just said that before you started with the research, they were already in the clinic. Well, the problem was the source. The source, up until recently, was dead bodies, dead pigs, dead cows, and even human cadaver. And that's not a very safe source. So the FDA, in 2007, already made a notice asking the companies to start to look for better and safer alternatives. So that's exactly what we did. We cloned all the 5 human genes. They make human collagen in human and introduce it into a single tobacco plant. So now the plant has the ability to make human collagen, identical to what we have in our body. That technology already came out of the lab. Today in Israel, we have a company called CollPlant. We have 25,000 square meters of greenhouses all over the country, from the upper Galilee, in the middle of the country, and the southern part of Israel. where the farmers receive these small tobacco plantlets that looks exactly like regular tobacco, except they contain 5 human genes that tells or teach the plant how to make human collagen. So the farmers grow these plants for about 50 to 60 days. We harvest the leaves. The leaves are transported by cooling trucks to the factory, where the process starts for extracting the collagen. Now, if you ever made pesto, you know how to make collagen. Just crush it with some buffer in a very big food processor. We get the juice, concentrated protein. The protein is then transferred to clean rooms in which we do the final purification steps. And the end result is collagen identical to what we have in our body, produced in tobacco, from which we make different medical implants. We have already 2 products that completed clinical trials, already sold in Western Europe and in Israel. One for diabetic foot ulcer, another one is an injectable product for tendonitis to repair soft tissues. And so you may say, well, plants are really great and they do great things for us. And I'm going to say that plants are not the only one. In fact, any kingdom that nature gave us brought us some really wonderful things. And this creature, which I really like, is called the cat flea. I've been the focus of our lab for almost 18 years. And one reason why I'm so excited about cat fleas is because their ability to jump. They have the ability to jump as high as 100 to 200 times their height. And I used to say, this is not exciting, but yet if you think about it, this is the equivalent of a person standing in the middle of Manhattan in a single jump, go to the top of the Empire State Building. So you will have to admit that this is remarkable. And many people would like to be able to do that. And the question is, how cat fleas do it? So it turns out that during evolution, they developed this wonderful protein, which is called resilin. Now, resilin, in simple words, is the best rubber on earth. You can stretch it, you can squish it, and it doesn't lose almost any energy to the environment by heat or friction. Everything is kept there for even a long time. So the cat fleas made their jumping pad from that material, and they store the energy there, and once they need it, they release it, and boom, up in the air. So you can imagine that those that didn't have good enough resilin are not with us today, because the cat digested them. But those that survived these billions years of evolution made this wonderful material that we wish to use. But here's the problem. To catch cat fleas is difficult, because they're jumpy, so it's not easy. But even if you catch few, you don't have much material. But in fact, you don't really have to catch many, only one. So what you need to do is just extract the DNA from the cat flea, and by genetic engineering, introduce the gene into a less jumpy organism, again, plant. So that's exactly what we did. In fact, we've done another trick there, because in cat fleas, it's a nanocomposite of resilin and another nanofiber, which is called chitin. And we prefer to work with cellulose, and I'll show you in a few minutes why. So we replaced in the gene the chitin binding domain with a cellulose binding domain. So now we have a new protein that we produce in plants and also in E. coli, in bacteria, that we can make nanocomposite with cellulose. So what can you do with that? A lot of things. Here we made a foam that is made of nanocellulose. I'll get to that in a second. And added to that a little bit of resilin. And look at the short video that describes the mechanical properties. So on the right-hand side, it's actually just a nanocellulose foam in water. So we squish it, it has only plastic behavior. And on the left-hand side, it's exactly the same thing, but now also with resilin. Look what happened. So even the students are excited. And you can do it again and again and again. It's funny, many people, when we get to this point, they start to laugh, and I think it reminds us, Humpty Dumpty, or one of those things from our childhood. Anyway, what can you do with that? We are now working with a Swiss company called On, only the Swiss company that would like to make sport shoes that have, for people that would like to have better performance. And you could think of many other applications. Well, we are in this meeting. Our main interest is wood. And again, as I said, Plant Kingdom gave some really wonderful things for us. Sequoia trees, for example, they stand there for hundreds of years, carrying hundreds of tons in cold weather, in hot weather, UV light. In fact, I'm not familiar with any plastic chair that can survive such harsh conditions. And yet, if you look at the structure of this tree and ask yourself, how come that it is so strong? How come that this tree is so well built? It turns out that it is made of this nanofiber, which is about 100 nanometer in length and about 5 nanometer in width, highly crystalline, very, very strong. Surprisingly, it's made of sugar. Well, it's not the same sugar we drink in our tea. It's actually a homopolymer of glucose, which is called cellulose. And these cellulose chains are organized in highly crystalline fashion to give this nanofiber, which is so strong that on a weight basis, it is almost 10 times as strong as steel. And yet, it's made of sugar. So analysts all over the world in the last 10, 12 years are really excited about nanocellulose. And they claim that nanocellulose is going to be one of the most important nanobiomaterials for the entire industry. Not just construction, but also transportation, air and space, medicine, sports, almost everything, even food, whatever you will touch in from 2020 or so will contain a little bit of nanocellulose for whatever reason. But here's the problem. 10 years ago, if you wanted to buy half a ton of nanocellulose to build a boat or do something like that, you couldn't find it. I mean, you even Google, you eBay, you even Alibaba, couldn't find it. And of course, you would find thousands of scientific papers where scientists like myself and others say, hey, this is a great material, but there was no commercial source. So we at the Hebrew University, together with a group from Sweden, Finland, Germany, and Italy, we formed a consortium in one of the 6 frame projects of the European community. And the idea was to develop a cost-effective method that can be scaled up to produce nanocellulose, and of course develop some applications. So the first thing we were looking for is a source of raw material. Of course, we didn't want to cut sequoia trees, and there is no reason, because cellulose is everywhere, and we found a very good source, and that's the sludge of the recycled paper industry. And why is that? Because we have a lot of that. And just to give you a feel, we have so much of that it practically covers our continents. Europe alone produces about 11 million tons of that sludge annually. This is the equivalent of a mountain 3 kilometers high sitting on a soccer field. And we make it in Europe every year. The Americans do the same, Chinese probably 3 or 4. And for everybody it's an environmental problem. For us it's a great source of raw material. So together with our partners from Sweden, from Luleå, we actually established a company called Melodia. Melodia is an Israeli company that joined together with Holman. Holman is, as you know, is a Swedish forestry pulp and paper company that came as a strategic partner. And we scaled up the process. And today we have a pilot plant both in Israel and recently here in Onsensvik, not so far from here. So we can now produce a nanocellulose on industrial scale. So what can you do with that? In fact, a lot of things. But all these things that you can do with nanocellulose boils down to the one very simple fact, and that just like any other nanobiomaterial, these fibers like to self-assemble. So above a certain concentration, when they are suspended in water, 2.5% or 3%, they start to form this chiral pneumatic liquid crystal structure. So once you apply that on any surface, can be a plastic or wood or whatever, or concrete, it will self-assemble and will form a very, very strong and transparent film. And just to give you a feel how strong it is, it's about twice as strong as epoxy resin. And remember, there is absolutely no covalent bond there. It's only hydrogen bonding and van der Waals interactions. In addition, if you add certain cross-linkers that are very useful in the textile industry, you can even increase the mechanical properties. In fact, if you look at the cross-section of this material, you can see very nicely that it is actually organized in layers. And between these layers, there are some gaps that enable us to introduce some other nanoparticles to change, for example, spectral properties or other physical properties of the films. So one thing that we have shown, for example, on the left-hand side, that when we add zinc oxide nanoparticles, we can effectively block the UV spectrum and leave only the visible range wide open. So that's very useful for packaging, for example, to protect materials from UV. But in addition, as you can see, nanocellulose in different formulations can be very, very effective oxygen barriers. That's another thing which is very useful for packaging. Nanocellulose can suspend things that are very difficult to suspend, like carbon nanotubes, for example. So all you have to do is take the nanocellulose, add it into carbon nanotubes, raise the temperature or sonicate, and all of a sudden carbon nanotubes are well suspended, and then you can make really either opaque or semi-transparent films, which have even some conductivity. So they can be very useful for other applications. More recently, we have shown with another group that we can now use these materials for LED lighting. You know that LED light, white LED light, is a result of use of filters that are made of rare earth elements and some very toxic materials. So we have shown that by mixing two organic pigments with the nanocellulose, we are able to form a very strong and quite effective coating to achieve a white lead that, as you can see at the bottom, is very, very stable, both at high temperature and in UV light. Another interesting application is for increasing strength of other fibers, like cotton yarn. We have shown that by only adding 1% to the weight coating cotton yarn, we can increase dramatically the tensile strength of the cotton yarn. And the toughness here, we've been able to increase by close to 300%. So one can make the same shirt that I'm using with 1/3 of the material, or maybe make a shirt for Superman. Well, sometimes we would like nanocellulose to be hydrophobic. So because the nanocellulose, of course, contain a lot of hydroxyl groups that can be easily modified, we have shown that by simple acetylation with the green chemistry, we've been able to make superhydrophobic foams and superhydrophobic nanocellulose materials that, again, can be useful for many things. Here, in this case, you see this almost an aerogel that has an extreme capacity to absorb organic materials. Here, we've shown that we can absorb about 200 grams of chloroform in only 1 gram of foam. So that can be used for oil spills and lots of other interesting applications. Another interesting feature of nanocellulose is its thixotrophic property, which brings us to 3D printing. Of course, thixotrophic is a very, very important feature for 3D printing. And here we've shown that we can print practically water at room temperature. By just adding 3% of nanocellulose into water and taking an STL file of butterscotch candy, we've been able to print this candy from water. Once you remove the water, it self-assembles into this nice foam and structure. Another interesting development is using cryo printing. Cryo printing is a very interesting principle where you can directly print your material on a very wet, on a very cold stage, which is controlled by Peltier. And of course, the trick here is, as you can see on the left-hand side, is an infrared camera that enables us to control the temperature right on the top of the printed material, because you want that the few 10 microns there will be still above 0 centigrade. Otherwise, it will delaminate. Okay, so by closing the circle, it then enables us to make the really nice structures. Another thing that you can do with nanocellulose is to do jet printing. And here we've shown by optical profile measurements that the reproducibility of these dots, and you can see here this ring or coffee ring-like effect that is made, and that in the beginning sounds like a bad thing, but actually it's a good thing because it enables us to print relatively light and strong material, and I'll get to that in a second. So you can see here that using different compositions of nanocellulose with other things, mainly simple sawdust from different sources, and together with xyloglucan and some hemicellulose. So all these materials were injected with no chemical binder. So everything here is made and extracted from wood. So no synthetic materials. And we've been able to use it in inkjet printing, binder jet printers, and also extrusion, combining different material, direct print, and so on. And the mechanical properties that you can achieve in some of these methods are quite significant. You can see here, these are, you see on the x-axis, this is the modulus and the density, and here the density and the strength of foams or oak. And you can see that we can achieve quite strong materials where the optimal was a density of 0.8 gram per milliliter, tensile modulus of 0.05 gigapascal, strength of 8 megapascal, and thermal conductivity less than 0.05 kilowatt per Kelvin. So I think that that we are really going into the right direction. And I would like to share with you a short movie just before the end of my talk that we prepared 2 years ago for the Biennale Architettura in Venice. We were fortunate to team up with a group of Israeli architects and presented in the Israeli pavilion a model. This is not real thing. This is just image. The real model was only 1 meter, and the camel also is not real one. But the idea here is to show what can we do probably in the future with nanocellulose 3D printing and combining materials. And I'll try to put it on, and can see the idea. So the idea here is to build a shelter in the desert. So the first thing that the first feature is a superhydrophobic coating of nanocellulose that enable us to collect some water early in the morning in the desert from the water dew. So we can collect this water into a pond. And of course, as you can see, because it's a self-assembled material, obviously we're not limited by the classic architectural constraints. We can make materials that all made of nanocellulose based that are either opaque or semi-transparent. And because we're able to introduce between the layers semiconducting nanoparticles and conducting nanoparticles, we can realize semi-transparent photovoltaic cells. So by doing that, we're not just introducing some light, but we can harvest some of the light to use this energy to operate this shelter. So we can use this energy, for example, to cool the water, and then the water will run at the floor, and so the people, when they walk on the floor, they will feel nicer, because at the end of the day it's desert. And of course, at night we can reverse the process and heat up a little bit. Now, the nice thing about all that project or idea is that at the end of the day, everything is renewable. So once we get rid of it, we're tired of that structure, all we need to do is to plow it into the ground, dig because at the end of the day, it's all made of minerals and cellulose, which are renewable. So I'd like to wrap my talk by saying the following. I really believe that we are at the plant age now, or at least at the verge of the plant age. Plants are at the bottom of the food chain, and they are able to produce everything. And not just collagen for implants, but or resilin from insects, but in fact, many other biomaterials that nature gave us. And using 3D or additive manufacturing technologies, we'll be able in the future even to make a heart. Now, that heart is not going to be as good as we can get from a donor. It will be better because we'll produce it from better materials. Now, you may say that you're a dreamer, this is something really for I don't know how many years, but I can tell you that we already developed a metac-related collagen suitable for 3D printing. And today, at Collagen in Israel, we have a project with 3D Systems, which is the largest 3D printing company in the US, and United Therapeutics. And we are now joined into a project that we are now printing a whole human lung. And this is not science fiction. In 2021, which is around the corner, we will be first in man. Admittedly, lung is relatively simple compared to heart. Heart is much more complex and many more cells. Architecture is much more challenging. But I think that maybe in 10 or 15 years from now, we will have another meeting here or somewhere else in the world. And the title will not be how to 3D print a wooden home, but maybe how to create a living home. And at the end, I'd like to quote Pavlov, who I believe said something very smart. Pavlov said that if you want a new idea, you should open an old book. And my addition to that is that the book was written. We don't have to reinvent the wheel. And the text is the DNA of life. All we have to do is read that text and start our progress from there. Thank you.
Thank you so much. While our next speaker gets ready, is there a question for Oded? At least two in the back.
And thank you very much for a really, really interesting talk. I was thinking right now, what is the market price for instance, this nanocellulose, and what do you expect? How do you expect it to develop in the next like 2, 3, 4, 5 years?
So right now, I think people are talking about, and I'm not the business development person, so I hope they don't kill me. But they're really talking about a few tens of US dollars or euros per kilogram fresh weight. Dry. And but the numbers, but it really because of the scale right now, and we believe that we will be able to drop it to few dollars per kilogram.
Thank you very much. Fantastic presentation. From your slides, I understood that you were mostly working with the cellulose nanocrystals. Have you also tested cellulose nanofibrils or microfibrillated cellulose?
Yes, absolutely. We are also working with the NFC, with the nanofibrillated cellulose produced by a microfluidizer. And this is done for another project that I didn't talk about, and that's food 3D printing.
Do you see a huge difference in the end user's product's performance between CNC and CNF?
Yeah, definitely. I think that they are, first of all, I think that both are legitimate, and there's certain things that you must have nanocellulose and other things that it's better to have NFC. I think that for a low haze factor, high transparency, most probably there is no competition with the nanocellulose or crystalline nanocellulose. But I think the fact that NFC can give you entangled fibers, it may have advantages in some other applications.
Maybe one day you will consider microfibrillated cellulose also.
Oh, definitely. Microfibrillated is, of course, a good one.
More sustainable alternative with a similar set of the properties, actually. Yeah, but thank you. Really inspiring.
Thank you.
Good luck with your work.
There is place for everybody.